In this section, we're going to look at Faraday's law. Faraday's law is stated in terms of magnetic flux. So let's start by defining magnetic flux. Magnetic flux. Again, is phi to represent it. Okay. So magnetic flux is a measure of the amount of magnetic field that crosses a loop perpendicularly. This is a measure of the amount of magnetic field that crosses a loop perpendicularly. Okay, now suppose this, let's say this is a loop like this. Now remember, the direction of area is perpendicular to the plane. So let's say this is the direction of the area, which is perpendicular to the plane of the loop. Okay, and let's say the magnetic field crossing the loop has this direction, the magnetic field. Okay, so the component of this magnetic field that crosses the loop perpendicularly would be this part over here, P perpendicular. Okay, so magnetic flux is defined to be the product of the perpendicular component of the magnetic field and the area of the loop. The greater the area where the magnetic field is crossing the loop, the greater the flux. The greater the perpendicular component of the loop, the greater the flux. So that's how the magnetic flux is defined. It's defined to be the product of the field that crosses the loop perpendicularly and the area of the loop. We're assuming the area is crossing everywhere like this. Okay, so we multiply by the area to measure the amount of field that crosses the magnetic field perpendicularly. Now suppose this is the angle between the field and the area. So you see, the magnetic of the field is B, so this component over here is B cosine of theta. So if theta is the angle between the field and the area, then this component over here, the perpendicular component, is the magnitude of the field times cosine of theta. Okay, so with that we can write the formula as flux equals the magnitude of the field, the area of the loop, times the cosine of the angle between the field and the area. Okay, so in this formula, B stands for magnitude of the field. Magnitude of the magnetic field. And A, of course, is area of the loop. And theta is angle between field and area. Okay, now before going further, let's look at the unit of flux. The unit of flux, as you can see from this formula, is the unit of the field, which is Tesla, and the unit of area, which is meter squared. Okay, so the unit of flux, magnetic flux, is Tesla times meter squared. Okay, now the area and the magnetic field are always positive. Okay, but this could be positive or negative depending on the angle. So if this angle is acute, so we're going to have a positive flux, but if this angle is obtuse, then of course this would be negative, and of course if this angle is 90 degrees, the flux would be 0. Okay, so let's look at some examples of calculating flux. Examples. Suppose we have the following. Let's say we have this square like this. Let's say this is 2 meters. Let's say this is 2 meters. Well, it looks longer, but it's okay. So let's say this is the field. The field is 5 Tesla. All right. So the question is calculate the magnetic flux crossing the loop. The magnetic flux crossing the loop. Now remember, the definition of magnetic field is, the definition of magnetic flux is amount of field that crosses the loop perpendicularly, but this field is parallel to the plane of the area, so it doesn't have a component that crosses this plane of the loop perpendicular. So we expect the flux to be 0, but let's see why is it 0 mathematically. Now the direction of area is always perpendicularly out. Okay, so in this case the direction of the area is perpendicularly out, a dot like this. So direction of area in this case is a dot because perpendicularly out. Okay, is perpendicularly out, which is a dot, right? Therefore the angle between the field and the area, which is this way perpendicularly out of the plane of the paper, is 0. Therefore theta equals 90 degree. Okay, so we have the magnetic field is 5 Tesla. That is 5 Tesla. We've told the area is, this is square, 2 times 2, so that is going to be 2 times 2, which is 4 meters squared. Okay, so the flux will be BA cosine of theta, that is 5 times 4 times cosine of 90 degree, but cosine of 90 is 0. Therefore there is no component of the field that crosses this loop perpendicularly, therefore the magnetic flux is 0. Okay, let's look at another example. Now suppose, let's say we have this circular loop like this. Let's say the radius is maybe 1 meters and the field is perpendicularly out like this, perpendicularly out of the paper. That's also that means, okay, perpendicularly out of the field. Okay, and let's say the magnitude is 10 Tesla. All right, now the question is calculate the magnetic flux crossing the loop. Calculate the magnetic flux crossing the loop. Okay, crossing the loop. Nice. In this case the magnetic field is crossing the loop perpendicularly. Okay, so we're told B is 10 Tesla, the magnitude of the field. The radius is 1, therefore the area is pi radius squared. Okay, so that's pi meter squared. Okay, now let's look at the area. Look, the direction of the area is always perpendicularly out. The field is also perpendicularly out. Therefore, they're parallel and the angle is 0. Okay, they're both perpendicularly out. The area is always perpendicularly out. Okay, and the field in this case perpendicularly out. They're parallel. Therefore, the angle is 0. Okay, so the flux is field times area times cosine of the angle. Okay, the field is 10, the area is pi, and the angle is 0. Cosine of 0 is 1, so we get 10 pi Tesla meter squared. Okay, so the flux in this case is positive. All right, another example. Now suppose we have, let's say, a rectangle like this. Let's say this is 2 meters and this is 4 meters. Now the field is suppose perpendicularly into the plane of the paper. Okay, so in this case the field is perpendicularly into the plane of the paper, right? And let's say the magnitude of the field is, let's say, 2 Tesla. Okay, so let's calculate the magnetic flux crossing the loop. Okay, calculate the magnetic field that crosses the loop, okay, so we have the magnitude of the field is 2 Tesla, and the rectangle has sides 2 and 4, so the area is length times width, that is 2 times 4, that is 8 meters squared. Now let's look at the angle. Okay, now the direction of the area is always perpendicularly out, but the direction of the field is perpendicularly in, so they're opposite. Okay, if they're opposite, the angle between them is 180 degrees. All right, so we have theta equals 180 degrees. All right, so the flux is field times area times the cosine of the angle. So the field is 2, the area is 8, and cosine of 180 is -1. This one is -1. So in this case, the flux is negative 16 Tesla meters squared. Okay. Now let's state Faraday's law. Faraday's law. Faraday's law said that whenever the magnetic flux crossing a loop changes, there will be an induced voltage which is equal to the negative rate of change of flux. Okay, so this law states that whenever the magnetic flux crossing a loop changes, there will be an induced voltage which is equal to the negative rate of change of flux, Okay, that is Faraday's law. Now let's use this one for induced voltage, or let's say induced EMF. Okay, then mathematically we can write the formula as follows. The induced voltage is equal to the negative rate of change of flux with respect to time. This is the mathematical statement of Faraday's law. The induced voltage is equal to the negative rate of change of flux. Okay, so if you have a loop like this, and if you somehow you're able to change the magnetic flux that crosses the loop, then there will be an induced voltage, and that induced voltage will produce current, or induced current. Okay, so there will be an induced voltage, and that induced voltage will result in current flowing in the loop, which we call I induced. If you know the resistance of the loop, then you can say the induced current from Ohm's law equals the induced voltage divided by the resistance, if you know the resistance of the coil. Okay, now this induced voltage could be positive or negative. So what's the difference between positive and negative. Positive induced voltage means the induced current is flowing in a counterclockwise direction. Negative induced voltage means the current is flowing in a clockwise direction. Okay, so positive E induced or induced voltage means the induced current is flowing in a counterclockwise direction. Counterclockwise direction, that's in the loop. And of course, negative induced voltage means the current is flowing, or the induced current is flowing in a clockwise direction, So that's the difference between positive and negative induced voltage. For example, in this case, you see the current is flowing in a counterclockwise direction, which means the induced voltage in this loop is positive. If it is flowing in a clockwise direction, that means the induced voltage is negative. All right, so as we know flux is BA times cosine of theta. Okay, therefore you can change flux either by changing the field, or changing the area, or changing the angle. Okay, so the magnetic flux can be changed by changing you see the field, the area, or the angle. By changing the field or the area or the angle. Okay, so these are the three different ways of changing the flux. You can change the flux by changing the field that crosses this field. For example, let's say you have a magnet over here. If you pull out the field crossing this will change, because the magnet is going farther and farther and so on. And if you change the shape of this loop over here, its area will change. So you could produce current or induced voltage using the field by changing the shape of the loop. Or you can just rotate it. Let's say you have a field of a certain direction over here. By rotating the coil, you can change the angle between the field and the area. Okay, so we're going to look at examples of producing voltage by changing the field, the area, and the angle. Okay, example. Suppose we have the following square. Let's say this is 2 meters and this is 2 meters, and it's placed in a magnetic field that is perpendicularly out, like this, perpendicularly out. Okay, now the question is, if the magnitude of the field, maybe let's say A, if the magnitude of the field is, let's say, decreased, let's say from 10 Tesla to 5 Tesla, let's say in 0.5 seconds. Okay, A, calculate the induced voltage. Calculate the induced voltage. All right, so now the area is not changing. Okay, So you can say the initial area equals the final area equals 2 times 2. That is 4 meters squared. Okay. The angle is also not changing because we're not changing the direction of the field, and the coil is stationary and the loop is stationary. So the area is perpendicularly out, the field is perpendicularly out, so the angle is 0. They're parallel. Okay, so the angle is not changing. We can say theta I equals theta final equals 0 degrees. Okay, the field is changing. It started from 10, then it went 5 Tesla. So that means the initial field is 10 Tesla, but the final field is 5 Tesla. And the question is to calculate the induced voltage. Okay, so we saw that the induced voltage is the negative of rate of change of flux divided by time taken. Okay, so that means the negative of change is final flux minus initial flux divided by delta t. Okay, so the initial flux would be initial field, initial area, cosine of initial angle, and the final flux would be B final, A final times cosine of theta final. But remember, the area and the angle are not changing, only the field is changing. Okay, so we can just say the induced voltage equals the negative of so you've got initial field, but the area and the angle are not changing, so I'll just put them like this: P final, A cosine of theta, okay, divided by delta t. All right, so we can factor this out. So this is negative A times cosine of theta, and then we've got this is final answer, final initial over here. So that's B final minus B initial divided by delta t. All right. So the area is 4. Okay, it's the same for the initial and for the final. The angle is 0. So you've got cosine of 0. And the final field is going from, the field is going from 10 to 5. So the final field is 5. And then the initial is 10. And the time taken is, that's delta t, we're told is 0.5 seconds. Okay, so delta t equals 0.5 seconds. So that is divided by 0.5 seconds. All right, now cosine of 0 is 1. This one is negative 5. Negative 5 times negative 4 is 20. Okay, and then divided by 0.5, we get 40 volts. Okay, the induced voltage is 40 volts. Now, let's ask a question. Is the induced current flowing clockwise or counterclockwise? Is the induced current flowing clockwise or counterclockwise? Clockwise or counterclockwise? Okay, now it's going to be counterclockwise because it's positive. Okay, so the answer is counterclockwise, clockwise, because the induced voltage is positive, because the induced voltage is positive. Okay, now let's say if the resistance of the loop, maybe let's put the direction over here, so the current is flowing this way. Okay, that's in a counterclockwise direction, the induced current. Now let's say if the resistance of the loop is 10 ohms, if the resistance of the loop is 10 ohms, let's say calculate the current, calculate the induced current, the induced current. Now from Ohm's law, we can say the induced current is the induced voltage divided by the resistance. Okay, so the induced voltage is 40, the resistance is 10, so that is 4 amps. Okay, so the current flowing in this loop is 4 amps. Now we're going to look at an example where we can produce voltage by changing the area of the loop, or by changing the shape of the loop. Okay, so let's look at another example. Let's say now we have this square. Let's say it's 2 meters. Let's say it's 2 meters. Now let's say the field is perpendicularly into, that's a cross, perpendicularly into okay. Let's say the strength of the field is 10 Tesla. Okay. Now the question is, if the shape of the square loop is changed to a circle, let's say in 0.2 seconds, calculate the induced voltage, the induced or EMF. Okay, we call EMF because in this case we are producing electricity just like a battery. Okay, all right, so the field in this problem is not changing. Okay, so you can say the initial field equals the final field, maybe just represented by B, that is 10 Tesla. Okay, the angle is also not changing. Okay, only the shape is changing. So let's look at the angle. The field is perpendicularly into the plane of the loop, while the area is perpendicularly out of the loop. Therefore, the angle is 180 degrees. Okay, so theta initial equals theta final. Let's just call theta, and it is 180 degrees. Okay, what's changing over here is the area. Okay, now the initial area obviously is a square, so it is 2 times 2. 2 times 2, that is 4 meters squared. How about the area of the circle? But now we're changing the square to a circle. Okay, so our final area is the area of the circle. Okay, now if the radius of this circle is r, then the final area is going to be pi times the radius squared. But how do you determine the radius? Okay, well, even though the area will change, the length of the loop is not going to change. Okay, that is, the perimeter of the loop will not change. Okay, so the perimeter of this circle and the perimeter of this circle should be the same. Okay, so perimeter does not change. Perimeter, or length of the loop does not change. So we know that the perimeter of this one is 4 times x. Okay, and the perimeter of this one is 2 pi times the radius. So you see, so we can say that the perimeter of the square, which is 4x, equals the perimeter of the circle, which is 2 pi times the radius. So that tells you the radius is 4 times the width of the circle divided by 2 pi, or 2 times the width of the square divided by pi. Okay, now in this problem the width is 2, right? So the radius is 2 times 2 divided by pi, or 4 over pi. So we know the radius of the circle, okay? For the final area, which is pi times radius squared, is pi times 4 over pi squared, okay? So that is 16 over pi meter squared, okay? So we have the initial and the final. Now we can do the induced voltage. The induced voltage is the negative of the rate of change of flux with respect to time, okay? And also we're told the time taken is 0.2, all right? Okay. So this is the negative of, remember in this case the magnetic field and the angle are not changing, so we'll just say b cosine of theta. Only the area is changing, so it'll be a final minus a initial divided by delta t, okay? We just factor this out because that's not changing, all right? So let's plug the numbers. This is the negative of the b, that's the magnitude of the field, is 10 Tesla. The angle is 180 degrees, okay? So you've got cosine of 180, and the area, the final area is 16 over pi, okay? And then the initial area is 2 times 2, which is 4, okay? So this is 4 divided by the time taken, which is 0.2, all right? So now cosine of 180 is -1. So this negative and this negative will cancel each other, okay? But this number over here is bigger than 4, okay? So this number is also positive, all right? So this is about, let's approximate by, it's about 5 point something. But let me just write it that way. So you've got -10. Negative times negative is positive, so you just have 10 times 16 over pi minus 4 divided by 0.2, and 0.2 is 1 over 5, so that is 50, and then you've got 16 over pi, which is 5 point something minus 4, okay? That is in volts, okay? So obviously this number is, let me approximate this by 3, so it will be about 5 point something, so the difference will be 1 point something. Let me approximate just by 1. So this is approximately, let's say it's about 5, and so 5 minus 4 is 1, so it'll be about 50 volts, okay, approximately, all right? All right. So what does it mean? The induced voltage is positive, implies the direction of the induced current is counterclockwise. The direction of the induced current is counterclockwise, okay? Counterclockwise. All right, so that means the current, the induced current will be flowing this way, all right? Now the other way by which we can change the flux is by rotating the coil, okay? So let's look at such an example, okay? Suppose we have this rectangle over here, okay? Let's say this is 4, let's say this is 2, okay? and this is the field where we just place it like this. All right, let's say the magnetic field is 5 Tesla. Now suppose we rotate this by 90 degree. Okay, so you get something like this, so that this angle is 90 degree over here. Now suppose the coil is rotated by 90 degree. Okay, suppose the loop is rotated by 90 degree. Okay, so the new orientation would be perpendicular to the plane of the paper. All right, okay, the question is calculate the induced voltage. Calculate the induced EMF. Alright, so in this case only the angle is changing. So the magnetic field is not changing, so we go initial field equals final field. Let's just call B, and that will be 5 Tesla. Okay, how about the area? The area is also not changing. We're not changing the shape, and that is half of this is a triangle, 4 times 2, that is 4 meters squared. Now the angle is changing. What's the initial angle? The initial angle is perpendicularly out like this, and the field is parallel to the plane, so the initial angle is 90 degree. All right, so theta I is 90 degree. But you see, as you rotate the coil by 90 degree, see the area is this way. When you rotate it, the area becomes parallel to the field. Okay, so the final angle will be 0. When this is rotated by 90 degree, the area and the field will be parallel. Okay, so theta final would be 0. So the angle is changing from 90 to 0 degrees. Okay, well, let's say this happens in 0.5 seconds. Okay, the loop is rotated, let's say, in 0.5 seconds. So our delta T is 0.5 seconds. Okay, so the question is calculate the induced voltage, and that's the formula for the induced voltage: negative rate of change of flux with time, or the negative of the final flux minus the initial flux divided by delta T. Okay, so it's the negative of, now remember only the angle is changing, so the magnetic field and area are not changing, so you can say cosine theta final minus PA cosine of theta initial divided by the time taken. Okay, so you can factor out BA, so you've got negative field times area, and then you've got the cosine of the final angle minus the cosine of the initial angle divided by the time taken, delta T. Okay, so now let's plug the numbers. Negative, the field is 5, the area is 4, and then the final angle is 0, so you've got cosine of 0. The initial angle is 90, cosine of 90 divided by the time taken, 0.5. All right, so you've got, this is negative, you've got negative 20, and then cosine of 0 is 1, cosine of 90 is 0, divided by 0.5. Okay, so that is negative 40 volts, negative 40 volts, and the induced current is flowing clockwise because the induced voltage is negative. So the induced current is flowing in a clockwise direction, because E induced is negative. Okay, so in this case the current will be flowing in a clockwise direction, like this. All right. Now let's look at another example. Suppose we have this solenoid over here. Okay, and then we have the coil going like this, and then we have like this. Suppose, let's say, this is the source. Okay, and then let's say we have over here. So because of this, we're going to have current that flows in this direction. Okay. Now suppose, let's say the length of the solenoid is, let's say, 0.2 meters. That's the length of the solenoid. And let's say the number of turns, that's n is, let's say, 100. Okay. Now suppose we have another coil enclosing it like this, right? And let's say maybe the radius of this one is maybe 0.01 meters. That's the radius of the solenoid. Okay, so the radius of solenoid is 0.1, the length of solenoid is 0.r. Let's say the radius of this one, of the big loop over here, is, let's say, maybe 0.04. So the radius of the loop, let's say it is 0.04 meters. Okay. Now, as shown, let's say a loop of radius 0.04 meters is concentric with a solenoid with, let's say, length is 0.2 meters, radius is 0.01 meters, and number of turns 100. Okay. Now the question is, if the current in the solenoid, is increased, let's say from 0 to 2 amps, let's say in 0.2 seconds, calculate the EMF, or induced on the loop. Okay, so now at the current changes, we're saying the current changes from 0 to 2 amps over here. What's going to happen is the field is going to change. Okay, the field of solenoid, if you remember, depends on the current. So when you change the current, the field will change. So in this problem, what's changing is the field. Okay, so both the area, we're not changing, the area is not changing, and the angle is also not changing. All right. Okay, so Now the direction of the area of the loop, if you use the right hand rule, the direction of the area is going to be to the right, like this is the direction of the area. Okay, you put your hands in a counterclockwise direction, the direction of the area is to the right. Now let's look at the direction of the field. You remember the right hand rule? For a solenoid, if this is the direction of the current, this is the direction of the field. Okay, so for this solenoid, the direction of the field is this way. This is the direction of the field. So it's in this case, the direction of the area is this way, the direction of the field is this way. So the angle is 180 degrees. All right, and the angle is not changing. So we can say theta initial equals theta final equals 180 degree. Okay, in this case, the area of the loop and the direction of the field are opposite, so our angle is 180 degrees. All right, how about the area? Okay, if you remember, the magnetic field just outside the solenoid is approximately 0. Okay, so there is no flux over here. There is no flux over here. The flux is only inside. Okay, so we have to multiply the magnetic field only by the area where the magnetic field is not 0. We have only magnetic field crossing this area over here. Okay, so when we multiply the flux, we don't use this area because there is no field over here. The field is approximately 0. So the flux is the magnetic field times the area over here. So our area is the area, the cross-sectional area of the solenoid. Okay, so the initial area and the final area are the same. Let's just say it's A, and that's pi times the radius of the solenoid, not the radius of the loop. So we can take this radius 0.01. Okay, so this can be 0.01 squared. Okay, so that is 1 times 10 to the power of -4 pi meter squared. All right, now the field is changing. How do you calculate the field? Well, if you know the current, you can calculate the field. The field of solenoid is given by the following formula. Remember this formula? The magnetic field inside a solenoid is mu naught number of turns times the current divided by the length. Okay, so the initial field is mu naught number of turns divided by L times initial current I. Okay, and the final magnetic field is mu naught N over L times final current. Okay, so we're told the current increased from 0 to 2 amps, so that tells you BI is 0. Current I is 0 and current final is 2 amps. Okay, now let's go to the induced voltage. This is the induced voltage. Induced equals negative final flux minus final initial divided by delta T. Okay, now the angle and the area are constant, so we can factor them out. So you've got A times cosine of theta, and then you've got B final minus B initial divided by delta T. All right, and that is negative A cosine of theta. You see B final is this one. Well, we can factor out this one over here, mu naught N divided by L. So the final, you get final current minus initial current. Okay, divided by delta T. All right, so we factor this constant out. So finally we have the following, that is negative A cosine of theta. We factor out this constant mu naught N divided by L, and then we just have the change in the current I final minus I initial divided by the time taken. That's it. All right. So now let's plug in the numbers. The area is 10 to the power negative 4 pi. So this is the induced voltage. Okay. So the area is 10 to the power of negative 4 pi. The angle is 180 degree. Cosine of 180 degree. This is a constant, if you remember, is 4 pi times 10 to the power of negative 7. The number of turns is 100, and the length we said was 0.2. Now the current, the final is 2, the initial is 0, divided by 0.2. That's the time taken for the change. It says change it in 0.2 seconds. All right, so that's it. Now this one is negative 1, so we're going to kill this negative. So the answer is going to be positive. All right. So this will give me, this ratio is 10. So you've got 10 to the power negative 4, 10 to the power negative 3, and then 10 to the power of negative 10, and then we've got 10 to the power negative 8. So this is, well, we've got 4 pi over here. 4 pi times 10 to the power of negative 8 divided by 0.2, or, well, the negative has gone away. It's got negative over here, so it's actually positive. So that'll be negative 1, that'll be negative 7. So that's 2 pi times 10 to the power of negative 7 volts. That's the induced voltage, right? Okay. And then we're going to look at motional EMF. Motional EMF. This is induced voltage produced by sliding a rod in a U-shaped conductor placed in a magnetic field. This is EMF produced by sliding a rod in a U-shaped conductor, placed in a magnetic field, Okay, so in this case what we have is, we have a U-shaped conductor over here, placed in a magnetic field. Let's say the magnetic field is made perpendicularly out like this, okay, like this. And then we have a rod sliding in this C-shaped conductor. Okay, suppose let's say it's moving this way with speed v. Now look at this loop over here. Okay, as this rod moves, the area is changing, the area of this loop. But remember, change in area changes the magnetic flux, and change in magnetic flux produces induced voltage, and that induced voltage produces current over here. So we're going to have induced voltage or induced current in this loop because of the change in area. So this is an example of producing EMF by changing the area of the loop. Okay, now let's try to get an expression for this one. Suppose let's say the location of this rod as it moves with speed v changes from xi, let's say, to another location over here, let's call it xf, and that happens in a time interval delta t. Okay, let's say suppose the rod changes its location from xi to xf, let's say in a time interval delta t, okay? And let the length of the rod be L, okay? So remember, in this case, the area is changing. Let's call the magnitude of the field B, okay? And the speed of the rod is V. This one is speed, all right? So the field, in this case, the angle is also not changing, you see? You got the magnetic field going up, the area is up, perpendicularly out, so the angle is 0, okay? So the magnetic field is not changing. We can say B initial equals B final equals B, okay? The angle is not changing, so you can say theta initial equals theta final equals 0 degrees. What's changing is the area. The initial area is the length times xi, okay? This is the distance from here to here, xi. Okay, so the initial area is the length of the rod times xi. This is xi from here to here, okay? Now it changes its location to xf. It changed location over here. The area is increasing to the length of the rod times xf, okay? So you've got length of the rod times xf, all right? So this is called motional EMF. So let me put E motional over here, okay? And I'm not interested about the sign, so let me just put absolute value over here. So we have it's absolute value, so it'll just be B final minus B initial divided by delta T, okay? Oh no, this is final flux minus initial, I'll put over here. Final flux minus initial flux divided by delta T. I took as a negative because I put this in absolute value, okay? So that is the angle in the field are not changing, so this would be B cosine of theta A final minus B cosine of theta A initial divided by delta T. All right, now we factor out, well, this is 0, so cosine of 0 is 1, okay? So we just have B over here. This is 1 because theta equals 0, okay? So we've got A final is L times X final, and A initial, this is also 1, and A initial is L times Xi divided by delta T, okay? So we've got the following: magnetic field times length, and then XF Xi divided by delta T. Now what does this represent? XF minus Xi is distance traveled in time interval delta T. So this is distance divided by time, okay? So this is speed, okay? But XF minus Xi over delta T is equal to the speed, okay? So the formula for the motional EMF, is simply the product of the field, the length of the rod, and then the speed. Okay, so in this formula, B is magnitude of field, L is length of rod, and V is speed of rod.